Inverse tan of x is one of the 6 functions they can ask you in the Maclaurin series question, which is question 8 in paper 2. And the Maclaurin series is this formula over here. It's in the tables, so you don't have to memorize it. And to get the Maclaurin series for inverse tan or for any function, you'd have to get put in 0 for x, then you differentiate once and put in 0 and so on, differentiate twice. The trouble with inverse tan x is it's the only function where this gets very messy very quickly, and you get a lot of u over v's and so on, and it gets very hard to differentiate after 2 or 3. So we actually don't use Maclaurin series directly to get the formula for inverse tan of x. We have to go to a plan B. And it can be done using Maclaurin series, but it's just the calculations get a bit awkward, that's all. So we go to plan B, which is here under the line, and plan B is to call it y equals inverse tan of x, and get dy dx, which is 1 over 1 plus x squared, and then to use this fraction here to see if we can get a formula which resembles the Maclaurin series formula. So that's our approach, and we do this by long division, because 1 over 1 plus x squared means the same thing as 1 divided by 1 plus x squared. So we start off here with 1 plus x squared divided into 1, and do our long division in the usual way. 1 into 1 goes 1 times. 1 by 1 is 1, plus 1 by x squared is x squared. When you draw a line and change the sign, or subtract downwards, whichever way you do it normally, and you get minus x squared, as the ones cancel, and start all over again. 1 into minus x squared goes minus x squared times. Minus x squared by 1 is minus x squared. Minus x squared by plus x squared is minus x to the power of 4. We draw a line and change the sign again, and we get plus x to the power of 4 here, because the x squareds cancel. Start off again. 1 into x to the power of 4 goes plus x to the power of 4 times. X to the power of 4 by 1 is x to the power of 4, and x to the power of 4 by x squared is plus x to the power of 6. And you get the idea after a while what's going on here, the pattern. 1 into, you subtract here again, and you get minus x to the power of 6. You subtract, and that gives you minus x to the power of 6 above the line. And there's an obvious pattern developing here above the line. We have just found out that if we divide 1 by 1 plus x squared, obviously it never ends, it goes on forever like that, but we know the first few terms, and we know the pattern as well, because it's going to be going up in even powers. 1 minus x squared plus x to the power of 4 minus x to the power of 6, and so on. So we can summarize all of that by saying, if we have a function y which is fx, a function fx which we call y is equal to inverse tan of x, well then f dash of x, or dy dx, which is the same thing, dy dx, just to remind you, means the same thing as f dash x, which is 1 over 1 plus x squared, can be written as this up here. A long division, if we just divide it in, we actually get it in a different format, in a series format, just like Maclaurin series. 1 minus x squared plus x to the power of 4 minus x to the power of 6, and so on. Now that brings us to the next step. So this is our starting point for the next step. And if we go on to a new whiteboard here, we've now got the result at 1 over 1 plus x squared is equal to 1 minus x squared. So we have just proved this while on division, plus x to the power of 4 minus x to the power of 6, and so on. And the reason we picked the function, of course, the reason we picked 1 over 1 plus x squared was because we spotted that when you differentiate inverse 10, you get 1 over 1 plus x squared. So going backwards, of course, if you go backwards, then that means if you integrate 1 over 1 plus x squared dx, you're back at inverse 10 of x. And that's the result we're going to use next. We have a formula now for 1 over 1 plus x squared, but if we integrate that formula, we should get the answer for inverse 10 of x. So if we integrate this, that's obviously the same as integrating the right hand side, which is now a long series, an infinite series. Dx. And as we saw on the last slide, that is when you integrate and go backwards, you're back where you started, which is at inverse 10. So let's integrate this now, and it's not very easy to integrate because we just integrate each term individually. If you integrate one, you just get x. If you integrate x cubed, x squared, you get minus x cubed over 3. And you get plus x to the power of 5 over 5. And minus x to the power of 7 over 7. And so on. So even when you integrate, there's still a very recognizable pattern here. It's going up in odd numbers. And again, every second sign is minus. So the next one, without even working it out, would have to be plus, and would have to be 5, 7, so it's going to be 9, x to the power of 9 over 9, and so on, which is of course inverse 10x. So finally we have a formula for inverse 10x as a series. There's our formula there. So that resembles a Maclaurin series, but we didn't get it using the Maclaurin series method. So just to look at the Maclaurin series again to remind ourselves what we're looking for. We're looking for a formula that looks kind of like this: different terms, term 1, term 2, term 3, and so on, added together in an infinite series. And we would normally use this formula, but we didn't this time because it's too complicated. Can be done, but it's too messy. So we used an alternative method of division, and we ended up with an equivalent formula, which is on slide 2 here, to this formula here. So let's put a box around that because we now have our formula for inverse 10 of x. So there's your Maclaurin series formula for the inverse 10 of x. Now the last time this question was asked in 2002, they didn't ask you to derive the formula, they gave you the formula and you had to use it in a question. And so, you know, but I mean, this derivation is certainly on the course as well. So let's now go to the next step, which is using the formula and see what we can actually use this formula for. So now that we've derived it, on the next slide, inverse 10 of x, let's write it down again and let's see what it's used for. So we just go back to the last slide and look at our result. It's all the odd numbers: x minus x cubed over 3, x minus x cubed over 3, plus x to the power of 5 over 5 minus x to the power of 7 over 7. Don't forget it goes up in odd numbers, plus x to the power of 9 over 9, and so on. Goes on forever. Obviously the more numbers you add on, the more accurate the answer gets. And we're going to see that this leads to some interesting results. One of those results is the following: pi over 4, which is 45. 5 degrees, or pi over 4 radians. Pi over 4 is the inverse tan of 1. Because the tan of 45 is 1, so the inverse tan of 1 is 45, working backwards. And if we just use this result for the moment, pi over 4 is inverse tan of 1, we notice that we can get another formula for pi over 4 because it just involves subbing in 1 for x in our formula. So put in 1 for x, we get 1 minus 1 cubed is just 1 over 3, plus 1 over 5, minus 1 over 7, plus 1 over 9, and so on. So we have this a pretty amazing result, and we'll discuss this in a second. Pi over 4, or let's actually multiply across by 4 now. If you multiply across by 4, you get pi is equal to 4 into 1 minus 1 third plus 1 fifth minus 1 seventh plus 1 ninth, and so on. But of course, you've got to keep adding on numbers forever here to get more and more accurate. And again, that's such an important formula, we'll put a box around it. We have now got a formula for pi, for working out pi. And the significance of this is, if you go way back to the first time you came across pi in maths, the first time everybody comes across pi is in relation to circles. If you divide the circumference of a circle by the diameter, you'll always get this ratio 3.14, which goes on forever. No matter how big the circle is, if you divide by the diameter if you divide its circumference by diameter, you always get this ratio 3.14 and so on, which is we call pi. And here we have pi turning up in a formula that has nothing at all to do with circles. The exact same number again, 3.14, which goes on forever. So it's one of these numbers that's kind of built into nature. It turns up in all sorts of strange places. There's a few numbers like that, and you know, it turns up in seemingly unconnected areas, like here in Maclaurin series, and as I said, it also turns up separately in the ratio in a circle. So that's a pretty amazing result in itself. What it also means, of course, is that now we have a way of working out pi to more and more accuracy if we just keep adding on terms here. And there's one problem with this, is that it doesn't converge very quickly to the correct answer, and you can just write down that as a note. So again, I'll explain what I mean by that in a minute. Doesn't converge. Pi quickly enough. What I mean by that is you could be adding on there forever different terms, and you're getting towards pi very, very slowly, and you get there eventually, but it's, as I said, very, very slow way of working out pi. But at least it's a starting point. It's one formula that we've got using the Maclaurin series. One formula for pi as a starting point, as I said.